And Christy, I'm a research engineer at the Western Cooling Efficiency Center here at UC Davis, so just across the street. And today I'm going to be presenting on the load flexibility of a residential multifunction heat pump using a dynamic press. Is this?
I think you may have to put it at the computer, maybe.
It may not. Let's just, we can.
Yeah, that's fine.
I'll just use the arrow keys.
Yeah.
So, so as far as motivation for this project goes, in California, we have quite a bit of interest in decarbonizing the electric grid. And as we push more toward a renewable energy dominated grid, we get kind of this strange load shape. So as more intermittent renewable generation resources like solar PV come online, they contribute to this trough here at midday in our demand curve where we have an excess of solar PV generation. And then that's followed by this peak here in the evening hours, which usually requires carbon intensive generation resources like coal-fired power plants to meet that steep demand increase. So what we want to do with load flexibility is take some of the demand from either the morning or evening hours and shift that into the midday hours to take up more of those PV energy outputs. Okay, and so we are trying to do this with a multifunction heat pump. So what this is one outdoor unit heat pump that's meeting the space cooling, space heating, and water heating needs of the residents. So this one is installed here in Davis in a 2,000 square foot single family home. It's a 4-time heat pump. And one advantage of this system is that it requires only one 30 amp circuit. So there's no electric resistive elements. So you're able to put this onto an electric panel in most cases without any type of panel upgrade. So that's a major advantage of this one that can increase grid electrification.
What's the average amperage savings, do you think, from being able to do that?
So when you say
Well, because you've got basically one device that's taking care of so many things.
You'll see some of the results like our peak power reduction, which can give you some insight into amperage savings if we're assuming cost of voltage. But
But that's for hot water, heating of the house, and heat and air conditioning of the home.
And space cooling, right?
Cool.
So in this particular study, we're going to be looking at the summer season only. So we have 3 out of 5 operational modes in summer. We do water heating, where we're taking heat from outdoors and projecting that to the water tank to heat up our water. Space cooling, where we're removing heat from the space and putting it outside. And then we have a simultaneous water heating and space cooling mode where we're taking the heat from inside the house and rejecting that into the water tank. So in that case, this outdoor unit is not used as a heat exchanger, it's just the compressor using the air handler and the water tank as evaporator and condenser. And that mode is 36% more efficient than trying to meet either of those end uses separately. Overall over the season. So we want to encourage operation in that simultaneous mode as much as possible, and we'll see some of that in the load flex algorithm. So for our communication architecture, how we're interfacing with the system, we have a cloud-based communication between our algorithm and our system components. So it's hosted on an AWS EC2 instance, and all we're doing is talking to the thermostats through an API. So there's no need for any additional on-site equipment, and we're also not making any alterations to the system control. So we're just sending set points to each of these thermostats. And for our rule-based control algorithm, some things to note, it's system agnostic. So because we're just sending out some set points, it's not taking over any of the controls that are proprietary to this device. It has really low computational complexity, and also it doesn't require any training data. So this is purely rule-based. There's no model, so we don't have to know very much about prior system operation. And the way that we're taking in a price signal and turning it into set points is with the Z-score. So all that is telling you where in a normal distribution a particular price falls. So how far from the mean in that distribution that price is. We calculate a Z-score and then we adjust it by finding the ratio of max to min price signal prices. And then we can multiply that by a load shifting severity factor to amplify or decrease the peaks in that price signal. And then we can add a set point bias factor if needed to skew the prices set points higher or lower. So that we take in the prices, run them through this, we get 5 different bins of set point signal for both the HVAC system and water heating system. And we apply this for each hour in a 24-hour period. So this is done once at midnight and it's giving you prices for the following day. Set points based on prices for the following day.
There's a question.
Oh, what's the question?
You want questions while you're going through?
Sure.
Is the bias, for example, in winter, you want to bias it towards the heat of the space, whereas in summer, you want to bias it towards the cooling of the space? Is that why there's a bias to those
So
set points?
yeah, it could, I mean, that's one application for that. Alternatively, if you have like a particular preference from a customer on having maybe a warmer space than a cooler space, you could skew the set points a little bit higher just to take into account thermal comfort of that particular person. Yeah, it's kind of case by case how you want to handle it in that case. Right, so I'm just gonna, we'll go step by step even on. All right, so the price signal that we're getting is coming from Lawrence Berkeley National Laboratory. It's from the Complex Hub server, and we are looking at summer, but here's the price signal for both winter and summer. So summer has a single peak in the evening hours, and then winter has 2 peaks, one in the morning and one in the evening, because a lot of times you have heating load early in the morning when it's cooler in winter. We're looking at summer, so taking that summer signal and translating it into our set points. We can see here that we've got a load up event at around 1 o'clock for both the water heater and the HVAC. And another alteration we made within our algorithm prior to this, all of this time would have been either an elevated water heater or reduced HVAC cooling set point, which is unnecessarily energy intensive. And also, sometimes you get a situation where you're not pre-cooled or preheated in the case of the water heater immediately going into the load shift period. So we delay that to the final hour before the set points start to reduce. There's also a small change in this, which encourages the simultaneous AC and water heating, which is if we ever have a call for water heating, this HVAC cooling set point will decrease by 2 degrees to force the system into the dual HVAC and water heating mode to take advantage of that energy efficiency increase. So to give you an idea of how this looks for HVAC load flex and water heating load flex, this is the HVAC portion. So for baseline operation, we're operating the system on an occupant specified schedule, and the system is occasionally turning off during peak because this particular homeowner is enrolled in OwnConnect. So any load shift savings that you see are actually on top of what's already taking place with OwnConnect. For the load flex operation, which is on the bottom plot, you can see the system cycles a lot less frequently as compared to the baseline day. And if you look around 7 a.m. there, that is one instance where the user actually maybe raises the set point periodically. And then right before noon, you can see the reduction in set point. That's one of the simultaneous AC and space cooling, or AC and water heating cycles. And just before noon.
So, sorry,
Yeah.
just quickly. So these customers, because they're enrolled in Home Connect, this customer, is already motivated to reduce energy consumption.
Yes.
So what we're seeing with this is technology-based instead of behavior-based
Yes,
load
Yes.
modification.
yeah, I would agree with that. And if people are unfamiliar with Own Connect, it basically just turns the system off for a specified amount of time every day. So it's another kind of demand response technology.
So that's not, it's not really behavior-based, it's like they signed up for that program. So it's basically thermostat, remote thermostat control.
It's still somewhat behavior based though, because I've done Home Connect and it's behavior in that there's a gamification to it where you're paying you money to do this.
Yeah, so, yeah, you're incentivizing someone. I mean,
Yeah.
this one, you could really say is behavior-based too at the end of the day, because if you're thinking of it in terms of the outcome on your bill, if you were on a dynamic pricing signal, you're kind of incentivized in a similar way. So I would say there's a behavior-based aspect with both of them, honestly. Yeah, so. And both of the, when you say tech-based versus behavior-based, can you give me what you're thinking?
Well, I'm just saying like the baseline operation is understanding the performance without this intervention, right? Before this intervention, before this technology intervention, the change out or this equipment, right? So it's just helpful to understand that when you say load flex operation, it's basically this equipment, the unique features of this equipment that weren't there before, right? So, but there was a behavior, already a behavior base. Like in other words, if you went in and you installed this with somebody and they hadn't been enrolled in Home Connect already, their baseline might be different and you
Right.
might have a bigger
Right.
change.
Yeah, exactly.
Okay.
In this case, if we hadn't had Own Connect, I would expect this to be better than what we had before, because yeah, there's already some degree of load flex present. So this is anything on top of whatever we already had.
One thing I want to add, Ben, is the baseline is not for a traditional system. The baseline is the same equipment.
Oh,
Should be
I
clear on
see.
that too.
Okay.
It's 1 year of data from this equipment, and then we have 1 season of load flex with this equipment.
Same
So it's
equipment.
baseline.
So it's the same equipment, it's just whether or not you have it in load flex mode
Right,
or you're optimizing for load flex.
yes.
Thank you. Sorry for the.
Yeah,
I
no, it's-
I have a question. I'm sorry, your name is Christy, is that correct?
that is my name.
I'm sorry, What-
Go ahead.
is this, I see fewer cycles here on the load flex operation on this HVAC equipment. So is this a single stage heat pump?
Yes, this is single stage heat pump, so we're assuming that the reduced number of cycles is just from the difference in set point during that time, and it, not needing as many cycles to meet that lower set point.
Okay, thank you.
Sure. And then, all right, and then water heater load flex. So this is the same day. This is just an example. We're gonna see results for a multi-day case so that you can get a better idea of how it looks long-term. For the water heater and the baseline operation, we're operating with a constant set point, and then for load flex, it's the same set points that you saw before. If you look right before 12, that's the water heating event that called for the reduced set point in the HVAC system and induced that dual HVAC and water heating event. So there are more of those because of our control sequence. And this particular day, we had no water heating use because of the elevated water temperature going into the peak demand period. Of course, that can change based on whatever the water demand is on that particular day. So that's why we're going to look at it over a multi-day period.
So what's the peak demand for water heating though? Isn't that during like 6 a.m.?
So peak demand for water heating is very dependent
It's very
on
variable.
the individual user. This particular house, during most of the test time, there is a peak demand around 8 p.m.
Oh.
Well, not on this day,
Yes, they
but on
shower
a lot of the days there are. Just
Okay.
from knowledge of the past data. But yeah, in this house, there was a morning and evening water heater use, but that's very dependent on the person. We're mostly when we talk about peak demand, we're just talking about it in terms of the signal and how that's interpreted. So instead of what you would normally have in, especially in California, I think we're all probably on a time of use rate between 5 to 9, which is just that step change during those hours. This one is, you know, a variety will ramp up and ramp down. So this is just taking that and interpreting it in a way that you can provide load flex in kind of a similar manner,
Okay.
but with more of a staged approach. So demand is driven by the price signal. Or peak demand, period, I should say. All right, so for our multi-day evaluation period selection. So here we wanted to make sure that we weren't comparing two groups of days arbitrarily without considering the weather patterns and water use between those 2 days, especially since summer in the previous year. So this is from summer 2023 and then baseline data from summer 2022. So the weather patterns between those 2 years, summer 2023 was significantly cooler overall than 2022. So if you just take those at face value, you already kind of have an advantage. So to get around that and make this more fair, we looked at cooling degree days between our low shift period and found a similar group of days from the previous summer. And we also made sure that those days had similar overall water consumption. So that's how we chose our 2 periods for comparison. And then resulting from that, for our water heating test only, so the first stage of this, we didn't do HVAC, just water heat. We had a 16% decrease in the energy use during the peak period and a 14% reduction in the daily cost. And then once we started load shifting with both water heating and the space cooling, we had a 29% decrease in daily system energy use and 12% reduction in mean daily cost. So
This is all the same equipment, right? Except for just your
same
controls.
equipment, yeah. And
Sweet.
one of them, we were just controlling the water heater. And then, yeah, the second, sunset wants to go.
Wow.
So those are our results. And that's kind of the end of this presentation. So if
That's
anybody has questions,
Is the water heating happening in a traditional water heating 33, 50 gallon kind of
yes.
body? So did you utilize like an old gas water heater and just rerouted the?
I wouldn't say it's traditional. So this system it's not made by us. We have a system that was manufactured by Valor Corporation, and the tank is it's not a pressurized vessel for one thing, which I guess
A natural gas one might have been.
a natural gas one would have been. So there's more, I guess, freedom there to tap things in and out of this tank. It has a refrigerant line coming into the tank, and then it's just a stagnant body of water. And there's a second line, which is the water line. So in effect, it's kind of like a large instantaneous water heater where the water that's in the depressurized tank is just holding thermal energy that's getting, transferred to water as it flows through those vents. So we're basically, storing the heat in that stagnant.
How many gallons of water in that tank, roughly?
55.
Okay, it's a big one.
Other
Yeah.
question about that tank? Oh, Teresa wanted you to go back to the other slide and just leave it there. At the last one, yeah.
This one.
Does it have the same problems as a tankless water heater in the sense that you need to descale it like every freaking 5 or 6 months?
Not that we've seen.
Okay.
Do you anticipate that happening at all?
What was the question?
Descaling the
Do you
water
need to
heater?
descale this thing constantly like you need to an instant hot water tank, which, these electric resistance hot water tanks, you have to pay a couple $100 every 6 months to descale them.
I know that's something that we had discussed in some of the meetings with Laura, but I don't know if there's been any.
We don't know yet, I
Yeah.
think is the answer. We're very curious about the potential need for descaling. I guess it's heating up the water to a little bit lower temperature than the water in the tankless water heater, at least like the water that's close to the walls of the heat exchangers in those two devices. So it might have less scaling. We're keeping an eye out for that.
Cool, yeah. Because if it has less, then it'll be it'll be a really good, it'll be an easier sell, for sure.
Might be.
There is this, the scaling concerns are two places. One is the storage water, and one is the actual domestic hot water that goes through the pipe. So those are two different. So in traditional cases, you will have a tank, and there is scaling that happens in the tank. But here there are two places water is present. So I think we have talked to the manufacturer, and the manufacturer intends to add some sort of chemicals to it, corrosion and stuff
Or
build
even
up.
like a sacrificial anode or something.
Yeah,
'cause
so
there's-
that's-
on both sides, you can
Yeah.
get skin.
Yeah.
So
Cool.
I guess we could say it's still being developed.
Yeah,
Probably,
it's a
probably
proper-
better than an instant, than those like than the
Yeah,
tankless ones.
Yeah.
Is what I mean.
It's
so
Probably better
far,
than that.
so far, yeah, we, I would assume so, just based on the temperature.
You have one, Paul?
My brother does, and I'm watching him pay half a yen to deal with it. And he's like, you ever have to do that with yours? I'm like, no, man, my gas, hot water, it just runs and works, and 15 years later, I have to replace the thing.
Are there any other?
Is this a commercially available setup that got installed in this house?
Yes.
And that was your baseline data was the first year they're using this?
Yes.
And it required completely rerouting then, where and how the water and these refrigerant lines ran between, right, in
The
order to do
refrigerant
this?
lines, yeah, for
Okay.
sure. Water, was there any rerouting supervision on water there, or was it just, because it's the same closet, isn't it?
Yeah, so keeping the same closet as there are some bigger advantages we saw with this technology. This was the first install of this technology, actually, the equipment.
Like anywhere in a
Yeah.
commercial application?
Yeah, exactly. So this was the first prototype, first pilot. The advantages what we saw was that like in comparison to like a heat pump water heater, which is the traditional heat pump water that are coming into the market from Rheem or A.O. Smith, you don't need to, if the closet is inside the house, you don't need to necessarily have a high voltage, dedicated circuit to run the heat pump, because you're just pumping refrigerant in and out, keeping the point of water in and out the same. And then like you don't have to deal with any kind of exhaust air that the heat pump would need, a heat pump water heater would need if placed in a closet inside the home. So those are like the two big advantages of having such a unit, which is like, connected to an outdoor unit outside.
In addition to the load shifting.
Of course. This is just talking from the equipment perspective.
Yeah.
Right.
That this is the advantages.
Is this product currently being sold in California that does all three of these? Why would it was okay?
Yeah, how many, let's see, there's a Lennar Homes, they have a bunch there, and then, two others that we've installed and hope to be doing load shift testing on at Bear Creek Housing Community in Merced, California, or, no?
Yeah,
And-
I mean, it's in Merced, yeah.
It's near Merced, it's kind of like now.
And our understanding is there's two of these types of multifunction heat pumps commercially available in California now. Sorry, this is Dave Vernon, colleague of Super Sheets and Christie's. One of them is this one, and another one from LG, and then there's a couple more that may be coming on the market soon.
Any other questions?
I wanted to say that we're very interested in doing this kind of work with some variable speed equipment, because that changes some of the options, and we're very interested in developing the rule sets or model predictive controls to take advantage of the benefits of variable speed equipment with this kind of load management algorithm.
And Dave, you mentioned the LG has a product, and then there's a few other ones that are on the horizon. Are any of those variable speed, or? they're all-
Yes, I believe the LG is variable speed, and Panasonic has a product like this that's currently for sale in Italy and Spain, and we're trying to convince them to bring it here. And there's also a number of air to water heat pump options that can do similar things, like the Daikin Altherma, or LG makes one. There's several others. So there's a few different combinations of one outdoor unit heat pump that can provide space conditioning and hot water that are commercially available or right on the cusp.
Are they competitive with price and installation to basically standalone versions of these?
That is what we would love to know.
Yeah.
From quotes from my own house, so N of one, yes, it's price competitive.
Cool.
We think that it's probably a similar cost, and in cases where the house would need an electric panel upgrade for separate typical heat pumps, this may allow them to get away with not getting the electric panel upgrade, which can cost between $5,000 and $30,000 in California. So in those cases, we expect this kind of equipment could be significantly cheaper than the separate equipment alternatives.
Dave, this is Vince with Daikin. Any idea, I would, being from Daikin US, I'm also curious to see how the Altherma will shake out on pricing. We really do not know that total install. But when do you think, you said you plan to study this with the variable capacity heat pumps. What's the game plan on that, on doing that study?
We will be doing right now we have this equipment, the single speed equipment, just getting installed in our environmental chambers laboratory to do testing. It's testing starting in the next couple days. Q4 we will be testing a Panasonic variable speed system in our chambers, and we also have a Japanese NEDO agency funded project to install that Panasonic unit on our EEI smart home. So we're starting that process right now. We don't have a funded project to apply the load flexibility methods to a product like this. So we've been shopping around. We're looking for grant opportunities or sponsors that are interested in moving that forward.
Thank you for that. And just to make sure that this study that we saw today, this was actually what you stated. I mean, this is a real home.
Yes, a real home. It is the home of one of our staff members, so we're intimately familiar with all the ins and outs. And yes, it's a real home, and
this is great. This is great.
We're happy to talk in more detail with folks that want to learn more. So, but let us know.
Nice, Christy. She's jealous. Oh, I'll take the. All right, Jonathan, you're up.
All right. Yeah, that's what we want. Are we good? All right, cool. All right, so I'm Jonathan Hollist, also from WCEC. I'm going to talk about the Desiccant enhanced indirect evaporative cooling and our laboratory testing. So, just the last presentation or in the questions, we talked about our labs. So I'm going to talk about some of our testing we did in our environmental chamber for this Desiccant enhanced indirect evaporative cooler. This was a unit made by Blue Frontier, and they are the company that is set up to run this technology. I gave this presentation at ASHRAE. I couldn't say the name of the company. I had to keep saying Desiccant enhanced indirect evaporative cooler. But here we can say it's Blue Frontier. They worked with us and the program to help get new technology on the market. It is the Cal Test Bed Program. So, what is this? This is a combination of two technologies. One is indirect evaporative cooling and the other is desiccant evaporative evaporation. And so a lot of people are familiar with direct evaporative cooling. This would be like a swamp cooler. You run hot, dry air across the wet medium. The moisture evaporates and you have cool, moist air. Now that can be effective in dry climates, but it can also be a little bit too damp for people. So more recently, a technology has come around that is an indirect evaporative cooler. What it does is it takes that cool, wet air and exchanges it with hot, dry air, and you get some cool, dry air. And so that's nice. That's a very good technology. We've tested it quite a bit at WCEC, and but it's still only limited to dry climates to be an effective cooler. So what this technology has done is added it with desiccant dehumidification. Probably the most well-known form of desiccant is like the little packages in pill bottles or in your food things. And that helps to pull the moisture out of the air. Well, what is done in this technology, it is a highly concentrated solution of the desiccant in liquid form. And when you run the air across that, it pulls the liquid out of the air and dehumidifies it. Funny thing that happened to us while we were testing, we spilled some of this stuff on the ground and made a big puddle. So we cleaned it up, we worked to clean it up. And usually when you spill something and there's a puddle, you leave a little bit, it evaporates and dries up. Well, this didn't happen. I walked away and I came back an hour later and the puddle was bigger again. And I'm like, what happened here? And then I remembered, oh, this is the desiccant. It's pulling the moisture right out of the air and it's doing exactly what it's supposed to. So we had to get it more diluted and clean it up finally. But if we can follow, the little setup here of the process, you have the mixed air. That would be the air that's coming from the outside with a little bit mixed with what's returning from the system. And it goes through the beginning and it gets the desiccant, pulls the moisture out. At the same time, it's pulling the heat out because the exhaust air is cool and it is pulling the heat out of it. And then you have the supply air that is dry and cool. It can also have any amount of moisture that you want. So that this makes a efficient and robust cooling. So we can cool and give the amount of moisture that we want based on the controls we set up for the system. And we can also save a lot of energy at the time. So in this system, we're not running any kind of compressors. We are just running fans and pumps. So that's not a whole lot of energy usage and it ends up being a very efficient system. Now, like I said, over time, the desiccant's going to lose its effectiveness. It's going to get diluted and lose its effectiveness, so it needs to be regenerated. Now, that doesn't have to happen in the real time of the system running. It can be done during lower loads, so you can have a very nice and easy load shifting energy storage. And sometimes they call this a thermal battery, or and so this desiccant could be held in a big tank of this solution, and it can just be weighted for when you need to cool at important times. You can do it during, you can regenerate it during low rate times.
How does it regenerate?
How does it regenerate? Heat.
Just,
So you had heat and evaporate out of it.
so you have to add energy then into it to.
Yeah,
to-
so there is another amount of energy that you got to add to it during the heat. The one that we tested actually had a radiant
Oh, sweet.
hot water heater. But that was not one that they want to use in the end.
Mhm.
So here's our little test setup that we did in our lab. So we have a environmental chamber, two parts to it, an outdoor and an indoor air chamber. For this particular one, we didn't really use the indoor air chamber, and we put the unit inside the outdoor chamber, and we set the system to the mixed air conditions that we want. We brought in the mixed air through the system, and it produced the supply air where we measured the details of the flow and the air, and then we measured the exhaust air. We also had the regenerator and the control unit outside. So if we looked on the left side of the picture, that's the regenerator and the control unit. We can see the big tank there, some flow meters, and some of the regenerator information parts. And then on the right side is the cooling unit, and you can see the different tubes and storage parts coming out as it goes through to cool everything. It's important to note that this was just a prototype unit and made for testing here, and they have some of the units that they're working in other testings that are more efficient and bigger and better. So we wanted to run a couple of different test scenarios in the lab to kind of see what we wanted to do or how it would work and how efficient it would be. So there were 4 different climate conditions that we tested, and then a few different mixing conditions within those climate conditions. And so our red dots are hot and humid air. So when we're running just all outside air, which would be similar to what we call a DOAS unit, dedicated outdoor air systems. On the hot and humid, it was similar to the climate in Orlando. And when in the very hot and dry, it was even hotter and drier than something would be like in Las Vegas. So we wanted to get a good overall span of those different conditions. At the bottom, you can see the particulars of each one. But I don't need to go into details of what all those are. So we ran it through all these different conditions, and we wanted to understand how the efficiency worked for the system. This is generally looked at as a coefficient of performance, or a COP or COP. And so we took the total energy cooled and divided that by the fan usage and the pump usage. And because this was a scaled down unit, we had a little bit of adjustment to each of those. And then the amount of energy used to control the system, which was very little, just the brains of the whole operation. And then here we use the regenerative power, which we got some details from tests that were done on a similar system at NRAL. If we wanted to look at just the real-time situation, we would run this same calculation without the regenerative power that was used. And that got some really high numbers because most of the energy is used from the regen. Yeah. So just a quick comparison of how this looks compared to some other items. So if you take the COP of a high efficient air conditioning unit, you get around 4. And then if you take the COP of a very good indirect evaporative cooler, you get around 20. So, in most of the situations, in our instances, we beat or came close to a high efficiency air conditioning unit, and then some hot and dry situations, we did very good compared to indirect evaporative coolers. So this is a good system that can help us understand or help us use in all climates, hot, dry, wet, and mild. So that was about what we did, just things that we can pick up from that. We have a wide range of climates that it'll run in. Good efficiency, even in humid climates. So one of the difficulties with indirect evaporative coolers has been, it has to be in dry areas. But now this system can work in all of them. In fact, the Blue Frontier company is in Florida. And so they do their testing and it works well for them there. Works well as a DOAS unit. So it can take in all this outside air and cool it and bring outside air to systems that will need it more often. And yeah, there's still some work to be done. Want to run a full comparison to baseline equipment, maybe a system that we know and have tested well, and compare how the energy efficiency works with those. Dynamic load testing for maybe big buildings when a lot of people come in, the room heats up, or maybe heating up through the day. And then different ways to regenerate the desiccant. We talked about maybe using a heat pump water heater or even waste heat.
Well, it's like a solar thermal.
Yeah, I'm sure it's possible.
Because I'm trying to wonder what the waste heat would be when you don't have a compressor, right? There's no compressor, so there's no where's the waste heat come from?
Yeah, there's some,
Okay.
right here in the exhaust air.
Oh,
There's some waste heat coming out of there. Or just from other systems, like if you're putting it on a big building
oh,
system,
that's true.
you can pull the waste heat off of some other system that's running.
So,
Yeah,
and this is the layer of, I guess, desiccant.
yeah,
So that gets cycled back for regeneration, right? Is that what's
Yeah.
happening?
mhm.
And that's like electric resistance for the test that you have done?
Yeah, and so the regeneration was, it didn't run usually while we were running the tests, unless we needed it for a long test.
Okay.
And then, we would turn it off and then run the regeneration and then, rerun another test.
Right. So for the COP calculations, you were just approximating the amount of time you would spend regeneration and calculating that power?
Yeah, it was based on, details from NREL, who had a similar type of regenerator, not the electric resistance that they had a heat pump on.
Okay.
So, I guess one of the drawbacks of dehumidification is comfort.
Yeah.
And so how are you able to control that, maybe an optimal level of moisture in the air?
So this wasn't something that I really tested with the controls on their system, but they have different controls of how much they mix and where they put the system through, whether they put enough through the indirect or enough through the moisture system. And then at this point right here, they can pick how much goes to exhaust and how much goes to the supply. So you can kind of adjust how much moisture and heat comes out.
So real time, they can, like, in other words, in a peak load event,
Mm-hmm.
right? When we wanna, I guess, there's a trade-off between the efficiency, especially the efficiency benefits
Mm-hmm.
with the dehumidification. Is it a direct? I mean, I'm oversimplifying it, or?
It gets somewhat old because of the desiccant, at least in here.
Yeah,
Yeah. So-
yeah, there was
And-
some, yeah,
I would just jump in and say, so this typical air conditioning equipment, it can't independently control the humidity and the temperature. If you want it to dehumidify, you have to cool down the air a lot. And so if you want it to dry out a space, you might end up overcooling a space, or in a lot of situations, while you're cooling a space, you end up doing more dehumidification than you've needed to do. So you kind of waste that energy that you spend doing the dehumidification. In this system, by changing the flow rate of the desiccant, you can do more or less dehumidification. And by changing the split in that supply air between the wet channels and the supply, you can change how much you cool the air. And so you have within a range fully independent control of those. And the overall efficiency of the unit, yes, if it's super dry and hot out, it'll operate like a really efficient indirect evaporative cooler. But the benefit is that it can still provide cooling even if it gets really humid. And so if you just have a few hours a year that get really humid, this could be great. Or if you want to load shift, even in Miami, you can choose to do the desiccant regeneration whenever you have excess renewables, and you can just use that stored dry desiccant to provide cooling when you don't have excess renewables.
But that load shift capability is primarily in humid environments. We're not getting that, how much of a load flex capability are you getting in California? I guess except if it's a humid heat wave.
right.
I mean, you can, so because you're doing that evaporation after you dry out the air, you can always do, there's always some humidity in the air, and taking it out will reduce the temperature of that supply air and give you more cooling. So you can still do load shift even if it's pretty dry. If it's really dry, basically you don't need to do load shift because you've got a COP 15 or 20 cooling going on. So you've made it so much more efficient. You've eliminated the cooling load basically.
Yeah.
So I guess I'm just trying to imagine that if you have a indirect system during a heat wave event, right? You're able to rely on no compressor based systems
Right.
altogether.
Well, unless you also need to regenerate the desiccant at the same time.
Yeah, provided you have a big enough desiccant well
Got it.
that you don't need to regenerate it.
But without the desiccant, like in other words, this is adding an ability to avoid using a compressor altogether.
Or to use a more efficient compressor, smaller compressor, in the case of like a heat pump regenerator.
And then to avoid running that compressor during the load flex moment.
Yeah.
Depending on the desiccant well, like you said.
Yeah.
I mean, I'm just trying to understand, because it sounds really compelling for a human environment, but it sounds like it's still applicable here. And so effectively, if this is combined with existing tech, this kind of eliminates the compressor load during a heat wave event. You can effectively do that. Is that?
Yeah.
Yep.
So I want to go back to your COP stuff. So the hot and humid, so that's with a heat pump, not electric resistance, correct?
Yeah, that would be based on
Okay.
like a heat pump one.
Got
Electric
it.
resistance did use
Would be
more.
like way worse.
Yeah.
Yeah, okay.
Wait, but this is the COP for cooling.
Yes, but you still have the desiccant.
And the desiccant, okay, yeah, the desiccant regeneration would be using a heat pump, and that
And this is 100% outside air?
This is a range. So the blue was like our minimum efficiency and the red was our maximum efficiency. I don't remember offhand which one it was, but it kind of mixed and matched which ones they were. But yeah, 100% outside air is part of it.
I would change too much.
Nah, I mean, if it's all hot, but you have some good return air that's going to help the system. Yeah,
We talked about this when you did the project, but
yeah.
is that room cooling capacity? Or is that capacity cooling outside air down, like the mixed air
Oh,
capacity?
I did both. And
I know,
don't remember
right.
what I'm showing
They're
here.
both relevant.
Yeah,
I would assume this is the mixed air capacity because,
yeah, because it would be, because we need different ones for the different various mixed airs.
right,
So if it was just room, there would only be 4 values here instead of 8.
if it were just room, well, there's ventilation air.
Yeah.
Yeah, but this would be the total COP, not just the room COP.
Yeah.
okay.
And I'm trying to remember what our outside air fraction was that we used to calculate the mixed air condition the chamber ran at.
Yeah, there were like 3. There was like 100 and there was a 50 and a 35, something like that.
Yeah,
That's all part of this calculation here.
Yeah.
Okay,
yeah. So kind of targeting
so it's more realistic.
just different applications, like
Different ventilation.
yeah, if you didn't have too many occupants in a space, you'd have a lower outside air fraction, maybe 30%-ish. And if you've got more, like maybe a classroom, you might be more towards 50%. Or if you want this machine to provide all of the outdoor air and run as a DOADS, then it would be 100% outdoor air.
Got it.
Cool.
Any other questions? Thank you.
Yeah.
Oh, yeah.
No, it's okay. We'll talk later. Yeah.
Go ahead.
Thanks, Jonathan.
Thank you. Cool.
Yeah, good job, both presenters. Thank you.